Okay, I had a few questions on the third assignment for this week. And this one's about the fundamental theorem of algebra. And I know the name of this may seem a bit intimidating at first, but this is the same type of work that we were doing earlier this year when we were solving quadratic equations. So anytime that we had a quadratic, our main goal was to factor it into its two pieces and set each of those pieces equal to 0. So that's exactly what we're going to do here. However, the instructions do tell us to find the number, so how many solutions, and the type of solutions, and then identify the real number solutions. And so with our notes, sorry I don't have a completed copy on this screen, but with our notes back here, the fundamental theorem of algebra starts talking about the different types of solutions and how they occur. And essentially what we were reminded of down here was that in a standard form equation, when the largest exponent is 4, that tells me that there are going to be 4 solutions to this example. And we have to go find out if they're real or imaginary or if there's some sort of combination. Similarly, in factored form, if we took the exponent of each factor, so there's an implied exponent of 1 here, this factor has an exponent of 2, and so I'm looking at 1, 2, 3 factors, and this factor here has an exponent implied of 1. Well, 1 plus 2 plus 1 is also 4, so that tells me in factored form this has 4 solutions. And so we should be able to tell how many solutions there are by looking at the exponents and looking at the factored form. We can determine if the solutions are real or imaginary based on the methods that are necessary to solve. Now in these first two examples, we've actually been very generous here. These are pretty straightforward. The problems have already been factored, so I see one factor here and one factor here, and traditionally we would set each factor equal to 0. So when does x minus 2 equal 0, and when does x plus 3 equal 0? Well, this tells me that there's a solution at positive 2. There's a solution at negative 3. And those are both real number solutions, so we've now actually taken care of this third part here. We've identified the real number solutions. As far as the number of solutions go, well, again, if I look at each factor and the exponent that's associated with each factor way back at the beginning, well, this factor here has an exponent of 1, or implied exponent of 1. This factor also has an implied exponent of 1. So 1 plus 1 tells me that there are 2 solutions. So that tells me the number of solutions that we should expect to find. And as it turns out, both of them were real. Real numbers, let's say. And so the type of solutions, we can say that both of them are real numbers because we found 2 solutions, 1, 2, and both of those were real. So the 2 solutions that were found in this particular problem are both real numbers. We'll see the same thing over here for number 2. F of x is equal to the factor x minus 4 with an implied exponent of 1, and the factor x plus 4 with an implied exponent of 1. So again, this tells me that there are 2 solutions. I don't know if they're both real just yet, so I'll actually continue to solve them. You might be able to tell if they're real or not, but a good practice would be to set each factor equal to 0 and then solve. So in this case, x is 4, a real number, and x is equal to negative 4, another real number. So we can come back here and say that there are 2 solutions. Both are real number solutions. Don't know why I'm having trouble writing this morning. Are real numbers. So both are real numbers, and the 2 solutions are positive 4 and negative 4. Now if we move on to the more complicated of the two, we take a look at problem number 3 here. Well, right off the bat, this is not factored, but that's okay because in standard form we know the solutions and the number of solutions by looking at the largest exponent of the polynomial. So in this case, there are going to be 5 solutions. And if you recall from the video, we could look at a graph of this, and we might do that here in just a minute. But when looking at the graph, we would expect to see this equation touching or crossing the x-axis a number of times, up to 5 times in total, because each time that the graph touches or crosses the x-axis, we found a solution to the problem. What I would do to solve this by hand, if requested, is to factor it first. And I notice that with these 3 terms that there is a common factor of x. So I'm going to factor that out. So f of x is actually equal to x times x to the 4th power minus x squared minus 20. Now, one of the concepts that we briefly talked about in the first unit was that functions, especially trinomials, can often be factored if they're quadratic form, if they're in the quadratic form. And in this case, I think we have that. We're so used to seeing just x squared as our leading term that we sometimes forget about this, but here's a trick that often works. X squared times x squared is another way to multiply to make x to the 4th power. And the numbers 5 and 4 will multiply to make 20. So if we treat this like a standard trinomial, I think we've got factor pairs that have generated the product of negative 20 and the sum of negative 1x squared if I use a negative 5 and a positive 4 here. So now that I've got this equation factored, I can set each factor equal to 0. So we'll say that x is equal to 0. We'll say that x squared minus 5 is equal to 0. And we'll say that x squared plus 4 is equal to 0. And we'll solve each. Well, that one's already solved for us. X must be 0. In this case, we can add 5 to both sides and then take a square root. Now keep in mind that we're looking for a number that multiplies by itself twice to equal 5, and that could be either the square root of 5 or the negative square root of 5. So think of this example. If x squared was equal to 81, x would have to be either 9 or negative 9. You should remember that from prior discussions. There are 2 numbers that multiply by itself to equal 81. So in this case, there are 2 numbers that multiply by itself to equal 5. Now in this third example, see here, I'll have to slide this over just a little bit. In this third example, we have x squared equal to negative 4 when I move the negative, or this plus 4 to the other side. And so x would be equal to the square root of negative 4, or the opposite, or negative square root of negative 4. And hopefully you recognize that taking the square root of a negative number is kind of tough for us to do. We can't normally do that. This is what produces our imaginary numbers. So from quarter 2 content, we talked about how to handle the square roots of negative numbers. We bring this negative sign out. So we have negative I square root of 4 and positive I square root of 4. So that negative sign comes to the outside of our square root symbol and turns into the letter I. And now we're left with something that we can actually find the square root of, or even simplify if needed. The square root of 4 is 2. So I'll call this 2i and negative 2i. We generally write them this way instead of I times 2 or negative I times 2. We tend not to write them in that form, and instead this way. So what I've seen now is that we were meant to find 5 solutions, and we have 1, 2, 3, 4, 5 solutions. And as it turns out, 3 were real numbers and 2 were imaginary or complex numbers. And if we jump out to Desmos just to take a look at this picture, I've got that prepared here. Here's the equation, x to the 5th minus 4x to the 3rd minus 20x. I'll adjust this scale just a little bit so that you can see the shape of the graph a little bit better. You'll notice that the graph does touch or cross the x-axis 3 times. It does touch at 0, and it touches at 2.62 2.27 and negative 2.627. Wonder if you have any ideas where that number comes from. Oops, and I just realized I had a typo in my formula here. Let me fix that. There we go. That's a little bit better. So again, solution at 0 and not 2.267, but 2.236. And again, I wonder if you recognize where this number comes from. Well, take a look at our work. We said that there's a solution at 0. We saw that on our x-axis. And there should be two other real number solutions that we see on our x-axis as well. And that's the positive square root of 5 and negative square root of 5. And if I pull up a calculator, let's see if I can pull one up here on my computer. If I pull up a calculator here, the square root of 5 is 2.236, and the negative square root of 5 would be negative 2.236. So these coordinates that are over here directly coincide with the positive and negative square root of 5. Now lastly, we don't see any other solutions on the x-axis. Even if I zoom out as much as I can, we never will see any more solutions on the x-axis. And since we won't see any more solutions, but the equation was written to imply that there were 5 solutions, well, if we only saw 3 of them, then that means the other 2 must be hidden or in what we call our imaginary number plane. And so that's why these last 2 solutions are solutions that contain imaginary numbers, because they exist in the imaginary plane. They don't actually exist in the xy plane as normal. So we'll never find these 2 solutions on a graph, and hence the reason for us to be able to solve these using traditional algebra. So I hope that clarifies problem number 3. Let's try problem number 4. With number 4, we see that the largest exponent is 3, so that tells me that there are 3 solutions. I don't know if they're real or imaginary yet. We should solve this by factoring in order to determine that. So there are 3 solutions. So I'm going to try to solve this by factoring before I go to a graphing calculator. And since there are 4 terms, 1, 2, 3, 4 terms, I might try the grouping technique from unit 2, from quarter 2. So within this first group, I see that there are, actually, let me try to give myself a little bit of space here. Move this out of the way. Okay, within that first group, I see that there's a GCF of x squared, so I'm going to factor that out, and I'm left with x plus 2. And in this second group here, I see that there's a GCF of negative 3. And that leaves me also with x plus 2. That's a good sign, because when these 2 factors agree, we can report that as part of our final answer. And so in factored form, I have x squared minus 3 and an x plus 2. Okay, so we've got this factored. We are to set both factors equal to 0. So when x squared minus 3 equals 0, and when x plus 2 equals 0, we will find solutions. This one's easy. Add 2 to both sides, and we see a solution at positive 2. This one's not too bad, but a bit more complicated. When we add 3 to both sides, we have to take a square root following that in order to isolate x. And as we said a minute ago, when we take the square root of a number, there's both a positive and a negative result. So I'm going to use this symbol to represent the positive and negative result. So now we did find all 3 solutions, 1 here, 2 here. So we'll make the comment that there are 3 solutions, and all are real numbers. And here they are. And if we wanted to graph that to confirm, we certainly could. And here we are with that equation. So if I adjust the scale just a little bit, we should see solutions at negative 2, like we had predicted. Whoops, sorry. I guess I made the mistake back here. Hopefully you caught that. We had to subtract 2 from both sides, so this should have been negative 2. It's a good reason to double check our work. I was in such a hurry that I missed that. But we have a solution at negative 2 and then plus or minus square root 3. Now the square root of 3 is going to be a strange decimal, 1.732. Let's see if our calculation is correct. On the graph, we have negative 1.732 and positive 1.732 as well. Now, it almost looked like there was a point in the middle here that was about ready to show up on Desmos. Keep in mind that Desmos likes to find maximum and minimum points as well. So don't include that as part of a solution. The only solutions occur along the x-axis. So I know that there was a lot to cover in the fundamental theorem. I do want to stress that it's actually very similar to what we've talked about in the past, but due to the more complicated equations, we do generally find more complicated solutions, and the process can be a bit more challenging, and I understand that. We will spend some time talking about this next week, of course, when I see you in class next. In the meantime, please do make sure that you continue to ask questions and send me messages through Schoology or email, and I'll do my best to answer them. Thanks for watching.